beta equals 90 degrees.
All right, hold on for 1 second. All right, so this is a loop, right? Is it what type of antenna?
Yeah, it looks like it.
A loop antenna?
I think so. Should be. It's in a loop antenna.
Yeah, this is. All right, so basically we've got a loop antenna like this in the XY plane, and here's and you're at a distance R equal what?
2K.
2,000.
2 kilometers.
2 kilometers, and this is at 90 degrees, right? All right, so go ahead. From there, they give you an H field equal to, my H is 5 microamps per meter, right? All right, this is a good problem. Pay attention to this one, it'll help you on the quiz. Go ahead.
Neglecting ohmic losses, how much power must the antenna transmit if it is
Short dipole.
short dipole?
Loop antenna.
Yeah, part A is a short dipole of lambda over 25.
That doesn't matter. It's a short dipole, and it's a small loop. You hear me on this? Short dipole, small loop. One thing you know for both of these antennas, the directivity, and we can assume unless there's a reason to include efficiency, and gain are the same. Directivity equals gain, and that's 1.5 times the normalized power density. Any electrically small antenna has a normalized power density of sine squared of theta, assuming either the dipole's in the z-axis or the loop is in the xy. Y'all follow me? So the maximum power density will be radiated at theta equal 90 degrees. Does everybody follow me? Right. For either a short dipole or a loop antenna, when theta is 90, you get the most. This is at 90 degrees, right? All right. Now, what we can get right away from here, and I want you to see what happens. First, let me put down a general equation for what the power density would be there if we knew how much was radiated. I'm following. So the power density anywhere, right, is equal to power radiated over what? 4 pi r squared. That's the isotropic power density. You all follow me on that? Then you multiply it by the gain, right? And since we're assuming gain and directivity are the same thing, it's going to be times 1.5. Right, times the sine squared of theta. Now that's the average power density, isn't it, class? Now take a note, if I have H, do I have the power density? Absolutely. From H, I have E as well, right? E is just equal to eta naught times H in magnitude. And the power density here would be equal to what? 1/2, I could put eta times H squared, or I could take 1/2 times E squared divided by eta. You all follow me on this? So if you have H, you have E, and you have the power density. Now, if I have the power density, come back over here. That's the power density I have right here. And I'm just going to put it as 1/2 eta times my H field squared. I'm just going to leave it as H squared. That's something I gave you, right? Now come over here and look on the other side. That's equal to P rad, right? Over 4 pi r squared. R is 2,000, right? Isn't that right, class? So we have R squared right here. Now 1.5 times the sine of the angle. The angle is 90 degrees. What's the sine of 90? 1, right? So it's just this times 1.5. You see we can get the total power radiated very quickly, can't we, class? The only thing we're doing is, you might call it reverse engineering. Take this equation, 1/2 eta times that H field squared. And did you try this one, Zach? Did the answers agree or not?
So,
How many tried that one? This is a great problem. It really is a showcase problem in terms of, it shows you everything you need to know about how to reverse engineer this stuff and find out what the power radiated is, regardless if it's a short dipole or if it's a loop antenna. If it's electrically small, you know the gain. Once you know the gain, it's over. I mean, directivity and gain. So here, if we wanted P radiated, we'll just get it, and we'll see the answer is correct. I'm going to say P radiated, that's what they're after, right?
yeah.
Okay, so P radiated here would be equal to, and I'll go ahead and put this down. So it's 1/2 eta, that's 120 pi. If you guys can help me with this, I'd appreciate it. Times 5 times 10 to the -6 here, and it's squared, so that takes care of that. Then I've got to multiply that by 4 pi r squared, That's 4 pi, and r is 2k, so it's 2 times 10 to the third squared. And then I have to divide by 1/2, or by 1.5, and so I'll divide this by 1.5. So over here, I'm gonna get the power radiated once. What is that? This is a good problem. I'm glad you asked that. Remember, electrically small is the key. I knew the game. You have to know the game for electrically small antennas. Either loops or gain directivity, because there's not really enough resistance. Anybody? I can't tell this just by looking.
One five seven.
0.1571. Is that right? You got it? Is that the answer?
Yes.
Okay.
Yours is 0.1579, but I just like that.
0.1579?
Right, yes. Very minor.
Close enough. All right. But you all follow me on how to do that. Now, if it was a loop antenna, it would be the same, because the directivity is the same. You all follow me? It doesn't matter how many turns. That's the nice thing. The total power radiated is what's multiplied by the gain to give you the increased focus. First you take total power radiated by 4 pi r squared. That's the isotropic density. Then your gain just sharpens it. Increases it or decreases it. It changes it by the factor of the gain. Now here's a question for you. Knowing that, what we just did, if I ask you now for the E field, say at a range of 4 kilometers, at an angle of 60 degrees, how would you get it? Just talk through it. Well, I know the power radiated, don't I? So once I know that, game on, it's over. I just go right here, change to the R I want, then appropriately it would be the sine of 60 degrees, not the sine of 90, right? So you're gonna have to adjust for that. That would be the power density. The power density is equal to 1/2 magnitude E squared over 80, you can get E, or 1/2 eta H squared, you can get H, either one you want. If you have EH or the power density, you have everything, basically. And remember, that's an electrically small antenna. This is a very good problem, okay? Anything else? Thank you for asking that. I was gonna go through this, wasn't gonna do that particular problem, but I was gonna go through it, because it really does showcase how you reverse engineer these things. And a lot of people fumble the ball on a problem like this. They'll say, we're not used to thinking that way. We're used to thinking, I got current or power right here, then I get all the other stuff. Instead of like, now I've got the power density or H field, and I want the power radiated. You all follow me on that? Okay. So next, I want to talk about, now I want to talk about arbitrarily long dipoles, dipoles of the order of a wavelength, then break it down to half wave, and then we'll get into monopoles. But this is where, now we're talking about practical antennas that are used all the time. And I might add, with wire antennas, something he really doesn't get into too much, but this is real important. The radius of the wire has a big effect on a lot of things. For instance, the radius of that wire has to do with how much power you can actually get on an antenna to launch, right? Second thing is that, and he doesn't talk about this much, the actual input impedance we're going to see will vary versus the actual radius of your wire that's used for the antenna, not the length of it. I'll talk a little bit more about this. When I teach EMC, we go through all of this in detail, because it does have a big effect on certain things. So now we're going to talk about, this is an antenna that's going to be, this is going to have a length L of the order of a wavelength. So it's always going to be center fed, and we're going to have a length L here on the antenna, center fed, and we'll assume that we know the current input there, I naught, right there. So if we come out a distance R away, and we did this proof last time, you all remember this? Where I set the whole thing up and I came down with the E field? We're just going to recreate this. So now the E field out here, this is the one you write down. The E field is going to be J60 I naught. So whatever that current is there, the center feed point, divided, or just times e to the minus j beta r over r. Alright, that's the That's how it varies versus radial distance. And then it's gonna be times this angular function. Now, in Whitworth's book, he uses that symbol to indicate, I could use a small f there, to indicate the actual weight on the angular function for power, but I'll use small f here. This one you don't have to memorize, but you use it often enough you can't help but know it. This is equal to cosine of beta L over 2 cosine of theta minus the cosine of beta L over 2 divided by the sine of theta. Now that's for, this is f of theta, that is the angular weight right there for the E field. And it would be in the theta direction. And of course I'm assuming this is the z direction, so I'm assuming the dipoles aligned at the origin in the z direction, just for simplicity. We can make all sorts of changes as required, but that's what it is. Now, the thing that happens here, to get the H field, I just divide this by eta, wouldn't I? In magnitude, so it'd be 60 over 125, or really, we have 1 over what? 2 pi. Follow me on that? Because if this is 100, if we're going to divide this by 120 pi, 60 by 120 is 1/2, right? And the pi would be under it. But y'all follow me on this? Then if we wanted the power density, the average power density, it could be given as 1/2 magnitude of that E field squared divided by eta, and you can do it that way if you want AR. Now that would be the average power density at a given range R, and if we wanted to normalize power density, what we'd have to do is figure out when this or what this value would be for the maximum. Now the only way you can get that is you have to take a derivative of it with respect to the angle and set it equal to 0. You hear me on this, class? And then you have to evaluate that value to see if it's either a peak or a minimum, or if it's a peak. And the peak value is what you need to divide that into this thing to get the actual normalized power density. Now, I'm not going to worry about that much. I'm going to just tell you that he has several problems in his book where he asks you to evaluate this and calculate the gain for antennas that are like, I think, 3/2 lambda long, maybe 2 lambda long, basically irritatingly long antennas where you have to go through and actually evaluate this thing and take the derivative, set it equal to 0, and then reevaluate what the value is, the peak and maximum value. I'm going to just say one thing. This is for arbitrarily long antennas. Generally speaking, when we talk about dipole antennas, the one that is most commonly used is the half-wave dipole. And the reason is because, first, the input impedance is about 73 plus J30 or 42.5 ohms, and we can easily get rid of that imaginary part, so we have a strict real part. So now from this one, I'm just telling you what it is for an arbitrarily long one. Then we get into, now we talk about, and this is the classic, L equals lambda over 2, or it's going to be a half wavelength long antenna. When you take a look at that, here's what happens. I've got L here, and this is range R, we got theta, we got I naught here. Now my E field, I don't think I did this one, did I? I didn't do the halfway. All right, so what you're going to get is the E field itself will be J60, and then it's going to be times E to the minus J beta R over R. Now this angular function simply becomes cosine, well, I'll put it in cosine of beta L over 2, we'll do this, times cosine of theta, minus cosine of beta L over 2, over the sine of theta. This is still a long dipole in a theta direction, but I want to show you how this thing changes, and for the better. If you take a look at this for a second, when I have beta L over 2, this is T. Well, beta is what in terms of wavelength? Anyway, it's what? 2 pi over lambda, is it? In terms of wavelength? So I can say beta here is 2 pi over lambda. Then I'm gonna multiply by 1/2, and then by the length of the antenna. Now, the length of the antenna is lambda over 2. Do you all follow me? It's exactly a half wavelength. So I put lambda over 2. Thing you'll notice is that cancels, right? That cancels, and I have pi over 2. Right? Follow me? So beta L over 2 is pi over 2 for a half-wave dipole. What's the cosine of pi over 2? What's the cosine of 90 degrees? 0. That goes away. Alright? And this becomes simply cosine of pi over 2 cosine theta. Now, I got a few comments about this. So this becomes cosine of pi over 2 cosine of theta over the sine of theta in the a theta direction. Here's the neat thing about that. This right here, this functional form right here, is very close to a sine of theta. So the beam itself looks about like the same. If we actually etched out the normalized power pattern, it'd be about the same. If you actually took a look at this, if I was to just show you what the actual radiated power density would be, I'd take that and square it, right? And then I'd have to take 1/2 the e squared divided by 8. If I normalized it, I'd end up with squaring this. By the way, the maximum value of this is 1, so it's like the sine. It makes real easy the calculation to get the normalized value for the power density. But if you actually looked at this, if that was the standard short dipole radiation pattern, just be a sine squared way, and you overlapped or replotted that with this, they're almost on top of each other. That's how close they are. You all hear me on that? So it looks just about like the radiation pattern for a short dipole. The difference is when we take the normalized power density, we would take, we go through and put 1/2 times that e squared divided by 8, and then we find the peak value of that and divide that into that to get the normalized power density. Do you all follow me on this? Once we have that, we find out it's equal to this. It's simply equal to the cosine of pi over 2 cosine of theta over the sine of theta squared. That's it. Just like for the normalized power density for the short dipole, it was sine squared theta, right? It's the same thing. Now, when you take that and you go ahead and get the directivity for D max for this one, that's 4 pi, and then it's the integral, it's a double integral from 0 to 2 pi, from 0 to pi, of the normalized power density that thing. I don't really want to do this. I'll just show you cosine of theta over sine of theta, and I gotta square this thing. Then it's multiplied by sine of theta, right, times d theta dt. That's the differential solid angle. Now when you do this thing, you got a sine squared down here and a sine here, so you retain 1 over sine. Then you got that cosine business there. Y'all follow me? Huh? Did you have a question? No. What I'm really trying to do is just plug in the normalized power density into the maximum directivity calculation. When you do this, I'll admit this. All right, one of these sines, that sine will cancel one of these sine squares, all right? Then you have one of these weird integrals, where you have a cosine with pi over 2 cosine of theta divided squared. You got to square that whole thing divided by a sine of theta. At that point in time, what I usually do is use Euler's identity and everything and mess with it until I can get into something doable. All right? You don't need to do that. I'm going to save you some time. This whole thing breaks down once you do it. And he says in his book, it's 1.64. In graduate courses, we do the whole thing. And at doctoral level courses, I should say. That's what it is. That's D max. Now, what was the maximum directivity for the short dipole or for the small loop antenna?
1.5.
1.5. 1.64. Very close, right? Not a lot of difference. Here's where the difference is for this. When you have this antenna right here, remember the radiation resistance for a short dipole was what? It was 80 pi squared L over lambda squared. And it was very small, of the order of ohms usually, right? Even if you get up to a tenth of a wavelength, it's still very small. For a half-wave dipole, an exact half-wave dipole, the antenna input impedance is equal to 73.2 plus J 42.5 ohms. Now, write that down. That's for an exact half-wave dipole. That's what it says in his book. The truth is, the radius of the wire used will affect this. It'll affect both this value and this slightly. This will always be about 73, 72 ohms. It'll be a little less sometimes. But this will start changing the reactance. Now, Dr. Winter's book does not address this. This is a little bit beyond the scope of what we need to go into here, but you should be aware of that. So don't, if you have 4-aught wire or something like a grounding rod thick antenna that's half wavelength, and if you expect to have exactly 72 or 73.2 plus J 42.5, if you cut it in the center and drill it, you're crazy. You'll never get that. Right? This is something for an ideal case for a very thin wire antenna. Now, here's the neat thing about this, and this, please get down. If you take that half, and this is in Dr. Winter's book, I think it's in the bottom of page 460. You can take a look at it and I'll check. If you take that half-wave dipole and you cut it down just slightly, and you make the length of this antenna L equals 0.485 lambda, then your input impedance will be about 73 ohms plus J nothing. All right? Which means you can get, you have basically no reactance there. All right? Normally, if you have a reactance, what you have to do is get rid of this. You would probably have to feed this thing with a capacitor that would have an exact value of minus J 42.5, because you don't want there. That limits current. What you want is the most current possible for a given voltage so you can throw the most power. That's the idea. But when you cut it down to 0.485 lambda, the electric field, the radiation resistance, obviously, everything is about the same. It is the same as if it was a dipole antenna. It's exactly a half wavelength, but with the benefit, you don't have this reactance. You don't want that. That limits current. And it's not good, is basically what I'm telling you. It's something that's an irritation. All right, that's what you want right there. And for a short dipole like this, it's 73 ohms. And I mean, when you make it 0.485 lambda, and that's probably the way it is in 99% of all the commercial applications. It's not exactly a short dipole. It's cut just a little bit less. Instead of 0.5 lambda, it's 0.485 lambda. It'll vary somewhat in length depending on, well, on wire gauge size. Now, has anybody ever been around any high power antennas in here? All right, well, the more power you use, generally speaking, the gauge of the wire goes up. And there's a lot to this. And some of these things are fed just by waveguides, and this is, I'm not going to go down that route yet. But when I was on the aircraft carrier Eisenhower doing work, this is in the summer of '87, I remember I made sure I took a look at all the communications equipment and all the radars that they had, all the old legacy rotating dish, parabolic dish antennas and stuff like this. And I noticed that for the communications antennas and stuff like this, they generally are they're not just real thin whip antennas, they're fairly thick, which I was a little amazed at, but they're also, I believe, unless they change them, I think they're hollow aluminum. They're not solid, because remember the skin depth thing? The center doesn't conduct current anyway. That was some of the things I learned, and what we're trying, I guess, what I'm trying to tell you is, when you're out there in the real world, a lot of this stuff is for ideal things that don't necessarily have a direct, they will not directly apply to your problem in the real world. You're going to have to go ahead and look at things that have to do with real applications. That's what I'm just cautioning you. So that's that antenna. Now, you asked about gain. So if I look on page 4, by the way, on bottom of page 460, you have your books here? If you look just under equation 8.85, it'll say something about, although the exact length depends on the antenna's wire radius, well, he does at least kind of hand wave it. A dipole antenna of about 0.485 lambda length will have an approximately 0 reactance, and it's just 73 ohms. Now, I would underline that. I think that's an important fact that's understated in this book. That's real important to know. You always want to get rid of that reactance. All right, now, back to your efficiency and gain question. So if you look at problem, example 8.5, and I wanna do this. Is his cut down to 485 then? I think it is, yeah. Alright, so hang on, we'll take a look at this, because this really is good at showcasing efficiency. I mean, they have an antenna like this, and here it's cut down, thankfully, to 0.485 lambda long, and then he has a source resistance, I believe, here, and then he has a voltage source here, right? And what's this voltage source value? 12 volts. So 12 volts peak. Is RS 25 in this? Yes. All right. And we're going to go through. And what's the kind of wire? Give me the other specifics. Is it some? It's got to have an American wire gauge reference somewhere in there, or a radius or diameter or something. Come on. So take a look. Oh, I'm sorry. I thought this is the one where, I'm looking at the one above it, in example 8.4, pardon me. Let's find the efficiency and max power gain for a halfway dipole antenna constructed with 20 gauge, this American wire gauge 20, operating at 1 gigahertz. So here's the real thing that he does. I'm just gonna tell you this one. We're gonna assume it's here. We're gonna assume this is it 20 or 40 gauge? 20. So we're gonna assume this is 20 gauge. It's really AWG, or American wire gauge 20. Now, for that one, he's gonna say the dissipation resistance, or really this is loss, it's the same thing as R loss. It's gotta be proportional to the length of the antenna divided by the conductivity, divided by the area it's flowing through. Now here, he's going to take it as the entire cross-sectional area, so that means the skin depth, wait a second. Okay, make a long story short, he's not even going through and calculating the skin depth, he's just saying that the area, the effective area, the cross-sectional area here, S, is of the order of, it's something times 10 to the minus 9 meters squared. What was the value in front of that? 5.33. So he's saying, after you account for skin depth, this is the surface area that the current's flowing through. Y'all follow me on that? Now, he goes ahead and gets this calculation, he finds a value about 0.533 ohms? 485. 0.485?
Yes.
Okay. If we have that, and we want to calculate the efficiency, and this addresses your question right there, the efficiency for this one would be simply the resistance of this antenna. This is going to be exactly 73 ohms if it's cut down, divided by 73 plus, you can tell me what this is, it's just about 0.99. What do you get for this? Can I have it as a yes? He may have it as just B, doesn't matter.
0.993.
All right, so that means the true gain of this antenna would be the ideal gain, which would be 1.5 times the cosine of pi over 2 cosine of theta divided by sine of theta squared times that, which is 0.993, which is about 1.5. All right. Now, if it gets down much less than that, if you're talking about 0.95, 0.9, then things get a little hairy. You need to redo that antenna design. All right, but this, it's not much dissipation loss. The real key thing is that the input peaks of that thing is in the 70 ohm range. So the losses you're going to get are insignificant. If that was down to like 1 ohm, then things change. Then you got some serious loss. Okay. That's the second thing I wanted to do. So I covered arbitrarily long dipoles. Now I covered the ideal, all right? I mean, the ideal half-wave dipole that has 73 plus J 42.5 ohms. Then the one that's shortened, and the gain for all, I mean, the maximum directivity on those are all 1.64. Now, what we're going to do is talk about monopole antennas. Now, I have to do a couple of things before I can get right into monopoles. One of the things I got to tell you is almost everything out there that's an antenna radiator that has a vertical antenna arm uses the ground to create an image, and it always has some sort of the ground used for an image. And if you don't know what I'm talking about, you're about to find out. So, what do I mean by that? All right. Here's exactly what I mean by it. You didn't get this in EMAG 1, I don't think. I wish you did, though. Normally, if you had just a chunk of charge up here, right here, and it's at a height, say H, above a ground plane, perfectly electric ground plane. This is just plus Q. If you were asked to solve that problem, if I wanted to know the electric field, say the voltage of the electric field everywhere, how would you get it? Just talk to me. You don't have to do it. I'm just asking, how would you approach that problem? You got a perfect ground plane, somebody sticks a charge above there. How do you go about getting the electric field or the voltage? Anybody?
Probably Gauss's law.
Well, Gauss's law says what? It says the integral of the charge, right, inside a region is equal to d dot ds over the surface, right? But it assumes a symmetric charge distribution. We don't have symmetry here. We've got a ground plane. Right. What you'd actually do is probably solve del squared V equals 0 all outside here, and then set the boundary conditions equal to 0 volts here. All right? This is a classic problem we do in graduate courses and stuff like that. So you would have to have this represented by a delta function of charge. Now, I'm not going to go down that route. It's a little tedious. It's a pain, is what I'm telling you, but you don't have to do that. Here's what you can do. This entire problem simplifies, it's mathematically proven. I can take this charge and I can go below that plane and I can put an image charge at a depth h here, make it minus q. So if that's plus, this is minus q, right? Then I can assume if I wanted the voltage, say above this plane, if I wanted the voltage at some point, say the distance was from R1 here, and the distance from this one, that point is R2. I can say that voltage at this point for R1 and R2 would be functions of X, Y, and Z and stuff are just going to be equal to Q over 4 pi epsilon naught, and then it would be 1 over R1 minus 1 over R2. Y'all follow me? Now, that eliminates all that del squared crap and all this stuff where you have to go through and find series solutions. R1 and R2 will be functions of X, Y, and Z. Y'all follow me? But that's easy to do. Then if you wanted the electric field, how would I get it? This is for electrostatics. Anyway. If I got the, there you go. If I got the voltage and I want the E field, I just say minus the gradient of V. So these would have to be functions of X, Y, and Z, and you would have to do a true gradient operation there. You follow me, class? But that will give you the E field. Now, the image thing is interesting, and pay attention to this. If I look at this, just to make sure I haven't lost my mind, what is the voltage when R1 equals R2, or when I'm right here on this thing? 0. Shouldn't it be 0? Absolutely. It checks that box. It's a sanity check. This works. So that works if we're dealing with just charges. Now, if we have currents, this is where it gets interesting. So remember, we're going after this monopole. If I have a perfect conducting plane, and I have a current that's vertically oriented, like so. I'm just trying to show you this roughly. Right. Well, if I have a current, where the current's going is going to deposit positive charge, right? Where it came from will have negative charge. Y'all follow me? Now, use the theory of images here. If I come down here, that would image as a plus charge. If I came down from there, that would image as a negative charge, right? Remember what I showed you. Negative to positive. That means the image of that current would be vertical. Y'all follow me on that? So if you have a perfect conducting plane and you have a current vertically upward above it, it will image in the same direction. This is important. Y'all follow me? How many knew that before? I don't think you get in physics, but this is real important. Did you get the method of images in physics at all? You didn't get an EMAG 1 either. That's unfortunate because it's such a useful technique. Now that's true for currents that are vertically oriented. What about horizontally? This is a perfect conducting plane. What about a current this way? Think about what I did. Where the current's going, images a positive charge, right? Where it came from, that's a negative charge. This is a real reasonable way to approach this explanation. There's a very rigorous mathematical proof, but it doesn't make any more sense than this does. Now, what is this image as? A negative charge, right? And this images as a positive charge, which means what? Now, the parallel currents image in the opposite direction. Vertical currents image in the same direction. Y'all follow? The final thing they usually do here is they say, well, what if you got a current that's got both components? So if I have a current like this, and I look below it, remember the vertical components image the same way. Horizontal opposite. So what happens?
Up and to the right.
Y'all see that? And that's how it would image. Are you with me all right on this one? Now that's important. So now, when I talk about monopoles, and we're gonna have to get this quiz. I didn't even get but I will. We're not getting thrown out, guys, so don't worry about it. You don't need to sweat anymore. Do me one favor, take everything off your desk.